This is part 4, Atomic Theory and Laws of Chemical Composition. We're making compounds now. And when we talk about compounds forming, we follow what we call the law of definite proportions. Which simply says elements combine in definite proportions by mass. Same compounds, molecules, same word, but one designates a whole lot of molecules. Okay, what does that mean? That means a given compound has a specific percent composition relative to the elements that are in that structure. It's called an elemental percent composition. Now understand up front here is that percent composition is true for every compound. It's 60% composition. But you can't use that to identify an unknown. You have to use a combination of things. So don't get that mixed up with product identification. So determine the elemental percent composition of whatever compound. You have, say, water or ammonia or sulfuric acid. Okay. What is the percent of each element in those substances? Okay. To do this, you need to, and many of you already know, you need to know how to calculate the formula weight. So the percentage is the mass of element divided by the molecular weight, or formula weight, let me put it that way before we go to molecular. Force times 100%. So if you understand how to do formula weight, this is very easy. But anyway, formula weight is the sum of atomic weights of the elements in a given structure. For example, H2O is composed of 2 hydrogens and 1 oxygen. Now, I round these off to the nearest whole numbers and run them out that way. To determine these specific figures you need for exam time, look at the answer choice. In the lab, you would always round everything to the instrument having the least number of sig figs anyway. So, long story short, I just go 2 times 1 plus 1 times 16, and of course this is in, right now, atomic mass units, and so that's 18 atomic mass units. Now we will learn about gram formula weight eventually, and we'll get to stoichiometry. But right now it's atomic mass unit. Okay, that's your total weight of the molecule. Now, when you talk about just hydrogen or just oxygen, we can calculate the percent of hydrogen is, we got 2 hydrogens in water times 100%. So all you have to do is substitute the mass, total mass of the element divided by formula weight times 100%. So in this case, it's 2 times 1 over 18 times 100%, and that's about 11% by weight. There you go. You just simply subtract it from 100 since there's only 2 in there. And once you get that, but if you have multiple elements, you got to go through and calculate at least up to the last one, and then you can add them up minus 100. So it's not a real mind bender calculation, but percent composition is very, very important if you understand how to determine a specific percent. So let's do that for this argument, a 3-element compound, just to give you an idea. Okay, the formula weight of H2SO4, to make a long story short, 98 atomic mass units. You punch in the numbers with it. But long story short, it's 98 atomic mass units. Okay, so the percent hydrogen would be 2 hydrogens, which is 1 atomic mass unit, divided by 98 times 100%. Just up a little bit. And percent sulfur would be 1 times 32 over 98 times 100%. And the percent oxygen, we have 4 oxygens, 4 times 16, 98 times 100%. Now always the sum will give you 100%, and the end of all the noise that we're making. So just for reference in your notes, you might want to jot these values down and just to have that look at. Go through. Any questions on that? And yes, chemical formulas nomenclature. Types of formulas are first. Well, you have molecular formulas, which reflect the actual number of elements within a compound. Next, you have empirical formulas. This reflects the lowest whole number ratio of elements in a given compound. An empirical formula may also be a molecular formula. CH4 is methane. it is both molecular and empirical. Because you can't reduce the subscripts to lower whole numbers from there. However, C2H4 is the C2H4 is the molecular formula, whereas CH2 is the empirical. Because you can reduce it to a smaller set of values in the subscript like that. Now, of critical importance here is being able to determine empirical formula from percent composition. You might insert empirical and molecular in here. Again, it's the smallest whole number ratio of elements within a chemical formula. And problems here will come to you in one of two ways. One, they'll give you some mass values, and from mass values, I'm going to give you an example here in a minute. You are to get the empirical formula. Or problems will come to you as percent per hundredweight, and from there you get an empirical formula. The essence of this calculation is to work really from the percent per hundredweight that will lead you systematically to the empirical formula. So what I'm saying is the mass values are then first converted to percent per hundredweight, and then onto your empirical formula. In that context, just to give you kind of a strategy issue here. Okay? So here are a couple of problems that are right out of the textbook, but they're very classic in their character. One comes from the 11th edition. Page 101. And it is number 365. Okay. And you're going to learn some things here that we haven't covered in total yet, and I will elaborate in great detail down the road, but it's important that you be able to do this calculation and as we go into future work. Okay, here it says an oxide of osmium, OS, is a pale yellow solid. If 2.89 grams of the compound contains 2.16 grams of osmium, what's the empirical formula? Glasses, so I can see what I'm doing. Okay, so we have mass of osmium oxide is given to be 2.89 grams. And osmium, mass of osmium, is equal to 2.16 grams. Okay, how much oxygen? What's the difference between the two? Obviously. So the mass of oxygen is 2.89 minus 2.16 grams. .73 grams. Now the idea is to take that and get to percent per hundredweight. So this would be part over the total. So this is the total mass, and these are your two parts, the osmium and the oxide. Okay, so percent of osmium would be part over total. And then the percent of oxy, you can do it by 0.73 over 2.89 times 100%, or the percent osmium from 100. So you can check your work by checking some of the individual percentages and so forth. Now, everybody okay on what I just did? It's part over total times 100, based on the given mass numbers in the given problem. At this point, you'll follow a systematic calculation, step by step, to leading to the empirical ratio and the empirical formula. And it is as follows. Very pat cross-section of how to do this. And they're all done the same way. Be very careful with your numbers, and you can get them all right first time through. And it's just one little variation that I'll show you as we get through this, and it's really easy to note. Okay. Now what this means is you take this percentage like that, and you convert it to grams. Well, if I have 100 grams, now watch this. If I have 100 grams, I'm in percentage. I know these percentages they're known. If I have 100 grams of the compound, how much osmium do I have? 74.74 grams. How much oxygen? 25.26 grams. So what I'm telling you is, what you start out with, say, osmium, up here, and oxygen, and we have 74.74% by weight, 25.26% by weight, and in grams, you just drop the percentage and put a G on it. Because the sum of will give you 100 grams. And if you have 100 grams, those are the parts of the 100 grams. So that would be 74.74 grams and 25.26 grams. Now here's a trick you may or may not remember, and we'll cover it in massive detail later on, is at this point you have to convert to what we call moles. Moles is the number of formula weights in a given mass. So if I have a mass here, I want to divide that by formula weight. How many formula weights are there in the given mass? I'll say that again. How many formula weights of the element are in the given mass? So that implies divide by the formula weight of the element. Well, this is 16 atomic mass units. I have to look up for some of them. 190.23. Everybody good on that? Now, don't get complicated. It's a mass in grams, and you ask yourself, how many formula weights are there in the given mass? That implies divide by formula weight, whatever the given mass is. Okay, so here are our moles of each element. Each of the elements. Now, in the sequence, you get to moles, you want to set up a ratio. Now, I combine these two in the following way. I'll show you how to do it. What you have is an osmium oxide ratio is what you're looking for. And so you have two elements. You had three elements. You would have element A, B, colon, C, and so forth. But it's a blank, colon, blank, like that. On the top, you put whatever mole values you have, 0.3929 and 1.5788. The next step is to reduce. When we reduce, that's normalizing toward the lower mole number. So you divide both of these by the smaller number. And it's on all problems like this. 0.3929 divided by the smaller number. And what that'll give you when you reduce this, it gives you the empirical ratio. So that's a 1 to 4 ratio. So this is your empirical ratio. And so it gives you your empirical formula, OSO4. And that's how you do it. Percent, the grams, the moles, ratio, reduce, empirical ratio, and write the formula. Write through that and memorize it if you have to. But as you go through this, you will better understand it. All right. So we have carbon. The way I set it up is carbon, hydrogen, and oxygen percentages per hundredweight. Carbon is 65.4%, and it is weight, but I'll leave them all. And then 5.5% by weight, and oxygen is 29.1% by weight. And you follow the same percent to grams to moles to the ratio reduced. You got your formula. So that'd be 65.4 grams, 5.5 grams per hundredweight, 29.1 grams per hundredweight. You divide by the formula weight. How many formula weights are in the given masses? Well, that's 12 atomic mass units, 1 atomic mass unit, and 16. Don't get fancy. You don't have to bring it out in long numbers. Okay, so now we want to set up the ratio and reduce. So I'll combine those two. We have a 3-element compound. So I want to have carbon to hydrogen to oxygen, 1 blank, 2 blanks, and a 3rd blank. And then we reduce that by dividing by the smaller of the set of numbers, mole numbers, and that normalizes it to the empirical ratio. So each carbon is 5.45, and it's 5.5 and 1.819. So we divide by the smaller 1.819, and so this leads us to the empirical ratio. That's 1 on the end. 5.5 divided by 3, 3, and 1. Okay? So this gives you a C3H3O empirical formula. So I've worked one from both directions, and the context of turning empirical formula. But the big issue is getting it to the percent per hundredweight and then going through a PAT procedure to empirical formula. Now, the only variation here is if one of these numbers, when you get to the empirical ratio, what you think is the empirical ratio, comes out to be 0.25, 0.5, or 0.75. Now, what that means is, say you have A, B ratio comes out to 1 to 1.5, or 1 to, well, I should do it this way, 2.5, or 1 to 1.50, or 1 to 1.75, because it will happen. There are problems which will show up when you do this reduction here, right here. They'll give you a thing, and you won't have anything other than that on test day. So, you know, it's really a cut and dried deal. If this shows up, you are supposed to multiply by 4 on that one, 2 on that one, and 4 on that one. And that will convert it to the empirical ratio, because it's got to be a whole number. Reduction right there, okay? So this will give you a 4, whatever, 1.25. 4 to 5. This is your empirical ratio, if those reductions come out in that capacity. And this will be a 2 to 3 ratio, and this is a 4 to 7 ratio, because you got to get that whole numbers. And the problem, in my experience, I've never come out with anything other than these variations. They'll either all come out real neat and 3, 3, 1, very neat reductions, or you'll have a little ratio in here. Okay. Now there are other problems in textbook determining empirical formula. Percent to grams to moles, ratio, reduce, and that gives you your empirical ratio in that order. So practice that 2 or 3 times, you'll have it, no problem. Count on problems in various forms in that. Now that just takes you to the empirical formula. What about the molecular formula? The molecular formula is a whole number ratio, a whole number multiple of the empirical formula, or molecular weight. Okay. So if we have mole weight, it will be equal to some n whole number, multiple, of empirical weight. Now, what typically is done is this is given in a problem. It has to be given. You can't work a problem like this. And you will determine the empirical formula and, of course, calculate the weight, and then solve that for the n value, and then distribute that n value through your empirical formula as subscript. Okay? Okay. I'll wait. They give you the formula weight of the molecule anyway. So I have to give you that. Okay, so where do we go from here? Find the mole. Carbon is divided by 12, hydrogen 1, and oxygen 16. And of course, you'll have a periodic table to reference and the values. Of course, this is 2.2. Here. That's also 2.2. And that's 4.4. So I mean, I'm rounded to make it simple. Okay. So now your carbon to hydrogen to oxygen ratios will be set up as follows. And we divide by the smaller of the set. And so that gives you a 1 to 1 to 2 empirical ratio. So this gives you your empirical formula, CHO2. So the empirical formula weight is carbon plus hydrogen plus 2 oxygens, which is 12 plus 1 plus 2 times 16 atomic mass units, 32, 42, 45 atomic mass units is your empirical weight. Right there. So now the N times empirical weight is equal to mole weight. And so N now is, look it up, it gives you 90 atomic mass units given, and 45 AMU is the empirical weight. And of course, that gives you a 2. That's your whole number multiple. So if you have CHO2, you want to distribute the 2 through, and your mole form therefore is C2H2O4. So it's just a matter of finding what that whole number multiple is and distributing it through the empirical form. Now there are more problems in the text on all 9, 10, 11 editions of it, and you can go online, determining empirical and molecular formula. Probably get 1,000 citations on working. Practice till you're comfortable with seeking it, and when we get to exam day, that'll be a gimmick. Writing chemical formulas requires that you have a basic understanding of oxidation states of the various elements, how to deal with it. I've given you some, and when I introduced you to the periodic table and the ion. If you have a metal, it'll go positive, and non-metals typically go to the negative in that in writing the types of formulas, there are two kinds of formulas. There are molecular formulas, primarily from here on, and polyion formulas. When you're talking about a molecular formula, the sum of all the oxidation states must equal 0. And the oxidation state we'll call a charge. And I'll use the symbol Q for the charge. And that must equal 0 for any molecular formula, a neutral molecular formula. For a polyion, the sum of all the charges must equal the net oxidation state. Now, you will understand molecular formulas. The sum of charges come out 0. But a polyion has a net charge in that, like NO3. Okay, that is a polyion, and it's a particle, a molecule that carries a negative charge. Or SO4, 2 minus charge. Or an NH4 is a particle that carries a positive 1 charge. So the sum of charges is a -1 for all the elements in here. And the sum of all the charges in here is a -2, and the sum of all charges is a +1. Now there's some standards that you would use until I otherwise tell you different. What we call the charge on oxygen, or oxidation state of oxygen, will always be a -2, unless I tell you different. Hydrogen charge will always be a +1 until I tell you different. There are compounds in which the oxygen will become a -1, and there are compounds that this will become a -1 called hydrides. But we're not going to use those for the short term. We're going to save those till later on. Anyway. So with this information right here, you'll have questions like, what's the charge on nitrogen? Or what's the sulfur oxidation state? Or what's the nitrogen oxidation state in a given point? Or PO4, 3 minus. What's the oxidation state of phosphorus in that? So you'll have problems like this. Or what's the oxidation state if you have another one, you have a molecular formula, H3PO4. All right, this is molecular. What's the oxidation state of phosphorus in that? Well, the sum of charges on that one will be 0. For the polyions, which you're going to memorize this weekend, and for Monday's quiz, you'll know what the polyion charge is. Because you're going to do what I say do, whatever. Okay, so let's just show you this one. Say phosphorus, PO4, 3 minus. Well, what does that mean? P plus 4 oxygen charges is equal to a -3. Well, make it an equation. Phosphorus is the unknown. Oxygen is always a -2. So now you've reduced it to that. So phosphorus -8 equals -3. And that gives you phosphorus to equal 8 minus 3. Or, believe it or not, it's a +5 oxidation state in that element. Okay, so you need to be able to deal with that. But you have to understand that are you dealing with a formula, a molecular formula, which sum of charges is 0, or are you dealing with a polyion, with sum of charges equal some oxidation state, net oxidation state? And when you calculate the individual specific oxidation state of an element, you line them up. Remember oxygen and hydrogen, because all of them are going to have oxygen and hydrogen except cyanide, CN, is a -1. And so that's only one non-oxo polyions that you'll have to deal with. Okay. Writing form. Okay, there are two classifications of compounds. We have ionic compounds and molecular compounds. If you're talking about ionic compounds, you're talking about two classifications: binary ionic compounds, CPDS, and polyatomic ionic compounds. Now, to write these, you need to understand what an ionic compound is in the first place. An ionic compound is a combination of a metal, something from the left of the chart, with something from the right, a non-metal. Now, polyions that are negatively charged are essentially the non-metallic part of the combination. So you might put in here a metal plus non-metal, where the negative is the negative polyion will be the non-metal. Binary refers to two different elements. Now, it may have more than two atoms, but if you have only two elements, aluminum chloride, AlCl3, well, you've got four atoms in there, but you only have two different elements, so that is a binary. Now, polyionic would be a metal, say like sodium, combining with sulfate, and you recognize this is the metal and that as the polyion. Well, some of them get kind of complicated, like potassium dichromate, like that. Well, who's the polyion in that mess? Okay? Well, the way you tell is when you have a multiple elements in a formula like this, from left to right, mentally isolate the first element, the metal. In other words, draw a mental line between that. This is your metal, and the rest of the molecule is your polyion, always. So you can separate those out, and you find that combination. So if you have a complicated looking molecule, kind of squint one eye and look at it and say, move the first one out of the way, the rest of it is the polyion. And so this weekend, you should know the charges on them and so forth like that. Neutral compounds, let's say, right, formula for potassium bromide. Well, if you look on the periodic chart, you'll see potassium in group 1. Well, that's way on the left side. And you'll find bromide over there on the right side, which is in the non-metal world, and one of the halogens. Potassium is in group 1, so potassium is going to lose one electron. Yeah? Okay, group 1 has one outer shell electron, is not going to gain 8, I don't know, 7, excuse me. Not going to gain 7, it's going to lose 1 and leave you with a plus 1 charge. And then you want to add that to bromide. Well, bromide's over there, it's got 7 outer shell electrons. Well, would you prefer to rip off 7 or add 1? That's the path of least resistance. That's why as you pass the carbon group, it starts adding electrons because the attraction in the nucleus is so strong that it prefers to gain electrons from carbon over instead of lose electrons. And so since bromide is in group 7, that means it has 7 outer shell electrons. So to get to the noble gas, 8 octet, you want to gain 1. And so by having 1 extra electron, it's going to carry a negative charge. So you have a plus 1 hooking up with a minus 1. And so when you put this together, you want the sum of charges to equal 0. Well, plus 1 plus a minus 1 does, in fact, equal 0. So that is, in fact, the correct formula for potassium bromide. We talked about aluminum chloride a moment ago. Let's say want to write a formula for aluminum chloride. So aluminum is in group 3. So it has 3 outer shell electrons, and it's in the metal collection. So we'll put a +3 on that. It tends to lose its 3 instead of gaining 5. And so the chloride's over there in the halogen department, and so it has 7 and prefers to gain 1. Well, +3 and -1 does not equal 0. So what do I have to do? I need 3 chlorides to neutralize the aluminum. So, and that's exactly what we will do. Aluminum and chloride, and we use a subscript down there. Now, subscripts are attached to fixed structure formulas. Now, coefficients tell you that you have multiples or higher numbers of a given fixed formula. But once you put that subscript in there, that subscript defines that substance as a compound with unique chemical and physical properties. You can't just change the subscript in the balancing equations and things. Once you put that in there, you can't change it because aluminum chloride is AlCl3. And you can't change that. It's just the nature of the structure. To increase or decrease the numbers of aluminum chlorides, you have to use coefficients, and you'll see that when we start balancing equations. I think most of you heard of that before. Anyway, what if you have polyions involved? And so you want to write sodium oxalate. Oxalate is C2O4 and carries a 2- charge. And sodium is group 1, carries a +1 charge. Well, you look at the net charges, +1 -2 will not add to 0. So I have to have 2 of those. And when I write the formula, it's a fixed structural formula. That's when I have to use the subscripts. So I'll have to use 2 of those right here, C2O4. And again, since that's a polyion, you can mentally isolate that, separate the first metal from the rest of the molecule, and figure out what the polyion is. And it's the oxalate, it's C2O4, 2468. I'm an oxalate. So you can remember that one easy enough, right? Okay. Sometimes the numbers of polyions in the structure, you have several relative to the cation structure. Aluminum sulfate. We want to write a formula for that one. That's a molecule. Some of the charges have to be 0. Aluminum +3 plus a sulfate. You can look 2- like that. 3 and -2, not 0. So what I have to do is I have to increase the number of sulfates and aluminums at the same time. Well, what I could do is I could look, this is just a trick. What I could do is write the formula together, aluminum sulfate, right there. And whatever the oxidation state of sulfate, or and +3 for aluminum, I can make these the subscripts. And that'll simplify it. So then we have aluminum subscript 2 and the sulfate SO4 subscript 3. But to keep from having 43 oxygens, you have to use a parenthesis in there. So you have to get used to that if you have a swapping oxidation states like that. But to check this, to show you, we now have 2 aluminums plus 3 sulfates, which is 2 times +3 plus 3 times -2, and of course that neutralizes and gives you 0. And so you need to get comfortable with writing ionic compounds like that. So you'll have a metal and a non-metal combination so that it will cancel to 0. So we've talked about 2 things. One, how do you find the oxidation state of an individual element, a polyion, given an overall charge? Okay, sum of charges may equal the oxidation state. or in a molecule. All right, how about this one? What is oxidation state of sulfur and H2SO3? That's sulfurous acid. We'll learn about nomenclature next time. Okay. So, since that is a neutral compound formula, then the sum of charges we know are going to be 0. So I have to take into account 2 hydrogens plus 1 sulfur plus 3 oxygens in here. And I told you that hydrogen is always a plus 1 until I tell you different. And then sulfur, 1 sulfur plus 3 oxygens, always a minus 2. And all that's going to be equal to 0. So now you've reduced it to an equation in one unknown. And so you simply, in this case, since it's a molecule, solve for whatever sulfur is, and so that's 2 plus sulfur minus 6 is 0, and so 6 minus 2 is equal to sulfur, which is plus 4 in this case. So while I've taught you oxidation states relative to individual elements and ions on the periodic table, once those elements begin to mix into the compound, they do not necessarily conform to the octet rule once they start combining. And that's another story that we will cover when we get to chemical bonding and why they are various oxidation states. Well, I'll reveal the rules on that at the appropriate time. But suffice it to say that once the element is buried in a polyion or buried in a multiple element compound, it may not conform to the oxidation states on the periodic table. But by themselves, essentially, they will. I mean, if you just have aluminum, you just say, what's the oxidation? Aluminum plus 3. Or oxygen minus 2. But sulfur, and some of them have multiple oxidation states. Okay, so the last topic here is, well, if I'm looking at a formula, some formulas have elements with fixed charge elements, and some of them have multiple charge elements. How do you deal with that? Well, copper, for example, has 2 oxidation states. It has copper plus 1 and a copper plus 2. So if you have to deal with that, you have to know what that oxidation state is. Well, here's a preview from nomenclature. You have to name that oxidation state in parentheses. Like if you're talking about copper chloride, you don't know, in that format, you don't know whether it's plus 1 or plus 2. But what is the convention is put a parenthesis after the metal and put it in there and put in the oxidation state in a Roman numeral, and that'd be copper. There's your formula, because that says this copper is a plus 1, and this says minus 1 all day long. Okay, and if you have copper 2 identified, chloride, then you would have a copper, and you'd have to put a subscript, because you'd have to carry 2 negative 1 to cancel out the 2 positive 1 on the copper. But those are called variable charge elements. Now, how do you look at the periodic table and tell who's variable and who's not when it comes to oxidation state? Well, it's not too difficult, but you will have to spend some time looking at the periodic table. fixed charge elements. This is the first topic. Which elements on that periodic chart will always have the same oxidation state forever and ever, and not change on test day. Okay? Group 1 is always a +1. No matter what, if you have a group 1 element, it's going to have a +1 charge. Group 2, no matter what, always has a +2 charge. These are fixed charge, no matter what shows up. You won't have a +1 calcium. There's no such thing. It's always a +2. On the other set that's in group are the halogens, except for acetane. These are always -1 in ionic compounds. Now, in polyions, they may not be -1s, but if they're by themselves in a compound, binary compound, aluminum chloride, aluminum bromide, potassium iodide, they're going to be -1s. So those are your group fixed charges. Now, you have some fixed charge transition metals that are always these charged forever and ever. Now, what you have to do to understand these is find silver in here. That's number 47. Right there. You start there, you got it. Because that's one block, right? And then go over to the right, and you have 2 blocks. Now, this is circumstantial, not scientific. But it is a memory device that you can depend on. Then one more step to the right, you'll have 3 blocks. The element with 1 block showing in this little triangle is always a +1. Silver is always a +1 charge. It has no +2 oxidation state. Never, ever, ever, never. Now you go over to the next 2 blocks. Those 2 elements always have a +2 oxidation state. There's no +1 zinc. Zinc always a +2, such as cadmium. So zinc and cadmium always have +2s, no matter what. If it shows up, you're working in a cadmium something or another, it's going to be a +2. You don't even have to, it's a no-brainer if you know how to count it. And then these are +3s. There are 3 blocks +3s. Well, actually, it's under group 3 anyway. But if you can find silver, silver's 1, zinc, cadmium's 2, then aluminum group's 3, right there. There's one more set, and you have to find tantalum. Now, that's not a +1. That is a +5. I mentioned it an hour or 2 ago. That's a +5. It is the only high-dollar ion structure that carries that high charge like that. It has 5 outer shell electrons. It'll lose them. And that, I'll show you, we'll talk about that in bonding. Come over 2 blocks to the left, conium and hafnium, and 3 blocks to the left, right here, like this. Now, the 3 blocks, conveniently, are +3 fixed charges. But zirconium and hafnium are +4s. So 4 and 5. So you're counting left to right, 1, 2, 3, 4, 5. Now, these are circumstantial graphics that I'm giving you in memory devices to help you remember, oh, those are fixed charges. So I don't need to expect any multiple charge. So if you were making a tantalum chloride, tantalum's always going to be a 5. And you're going to need 5 chlorides, TaCl5, that kind of thing. You don't have to put coefficients, I mean these parentheses with Roman numerals in them, because they're always fixed charges. Tantalum chloride, you don't have to put parentheses tantalum 5 chloride. You don't have to do that, because you're supposed to know that they are fixed charges. Okay. Everything else is variable charges. All the other stuff around there have multiple charges. Now, oxygen we've already talked about, and hydrogen we've already talked about. Now, until I tell you different, we'll throw that in as a -2. But all the others, when you're writing compounds, ionic compounds, will have variable charges. And the context of writing the formulas. Now, when you get over into over into molecular formulas, I'm going to save that till we start talking about nomenclature. Okay, so that's as far as I wanted to go today, how to just simply put together the ionic compound and what the charge oxidation states mean. Okay, I will open the lab in 15 minutes, and those that need to finish lab, and I'll assign you to a group that hasn't finished so you can see what they're doing. Okay, and you'll catch you up real quick. All right. Oh, fun. Am I wearing you out?
Yeah. Honesty is the best policy. It's all right. We'll see you Monday.
Yeah, no.